speed to market, and flexibility.
The goals of this program are to familiarize you with distributed object applications in Java. After viewing this, you should have a firm understanding of the remote method invocation architecture in Java, as well as the Internet Inter-Orb protocol and other Corba implementations in Java. Topics include an introduction to distributed applications, an overview of RMI, implementing RMI applications, an overview of Corba, and interoperability between Corba and Java. Welcome to our program on distributed Java. I'm Troy Downing of WebCal Corporation and also the author of Java RMI, Remote Method Invocation, published by IDG Books. On our agenda for today, first we're going to talk about an introduction to distributed applications. That's going to be followed by an overview of the Remote Method Invocation Architecture, or RMI, and implementing RMI applications. We're going to talk about an overview of Corba, or the Common Object Request Broker Architecture, and interoperability between Corba and Java. Introduction to distributed applications. In this section, we're going to have an overview of traditional as well as modern distributed applications. Now, in a traditional distributed application, such as a client-server architecture, we have very simple protocols, such as HTTP, or the Hypertext Transfer Protocol, RPC, which is a more complicated protocol, Remote Procedure Call, basic socket-based services, database servers, and very primitive distributed systems, such as SMTP, the Simple Mail Transfer Protocol, or Telnet, RShell, RLogin, etc. Now, in this first diagram, this is the Hypertext Transfer Protocol. This is probably one of the most simple of the distributed applications. We have a simple HTTP server, or a web server. We have an arbitrary number of clients. The clients request objects from the server, and the server returns them, objects such as HTML documents or images or whatever you would expect from a standard HTTP service. Now, in the RPC model, this is a little bit more complicated. In this graphic, first of all, we have a server side, an abstraction, and a client. Now, on the server side, we have the actual implementation of some code. This is where the work is done. On the client side, we have code that makes a procedure call. Now, all of this is facilitated by an abstraction layer. There's this thin layer in between these that maps the data types and the procedure transactions between these two systems, because the client may be a very different system than the server, and we may need to do the mapping between data types and procedure or method calls. Now, a standard database server, in this diagram, we have something a little bit more complicated than the HTTP server, but not as complex as the RPC model. Here we simply have an arbitrary number of clients that connect to this server that's attached to a database and delegates all of the database access. So far we've talked about procedure-based distribution models, but things change drastically once you start to deal with object-oriented systems. Now, as we see in this diagram, which is a little bit more complicated than the previous ones, we have two machines, machine 1 and machine 2. Machine 1 is hosting what would be traditionally the server side of a client-server application. Now, this server is an instance of an object. Now, in this object-oriented distributed model, a client needs to make sure that there is an instance of an object before it calls its member methods, whereas in an RPC-based model, it doesn't care because there's no object to deal with. So in this diagram, we have our object file, or our class file, that has these methods. On machine 2, we have this client that has a reference to that object, and through that reference to the object, it has references to the member methods of that object. So to call the methods on this remote object, it uses that reference to get to the methods that are actually called on that remote object that is running on machine 1. So the differences between an RPC-type distribution model and an object-oriented type distribution model are, first of all, an object needs to be instanced. You need to have an instance of an object before you interact with it. This is obviously not a problem in a procedure-based system. Now, the second part is methods are called on objects on remote machines. So you have a reference to this method, you call it on a remote machine, but it actually runs over on this remote machine, on what would be traditionally the server part of this model. Now, objects need to be passed by reference as well as by copy. As we saw in the previous diagram, we had a client application that had a reference to a remote application, so obviously we need to be able to pass references across the network. But when we're dealing with an object-oriented system, we need to be able to send objects as parameters as well. Objects need to be passed to methods, and objects need to be returned as return types. So this means that an object-oriented distribution model needs to handle object serialization. An object is inherently an abstract type, and we need to make that a very discrete type, or a series of bytes. It needs to be serialized so it can be sent over standard network connections, and this is what facilitates our objects as parameters. Now for an overview of the Remote Method Invocation Architecture, or RMI. In this section, we're going to have a high-level look at what makes up the RMI architecture. Remote method invocation is a pure Java solution for distributed applications. This is important to note. If you are writing a distributed application and you're writing it in Java, and all of the distributed components, all the different pieces of it, are also going to be written in Java, and you don't need to support any other languages or systems, RMI is really your best bet. There's no interface description language. If you remember, we saw a graphic of an RPC model where we had to have an abstraction layer between a client and a server for mapping different types of data. Well, in an all-Java environment, we know how the data is represented because it's all well-defined. So interfaces are described entirely in Java. There's no need for any third-party or third type of description language, which is actually really nice and facilitates rapid prototyping and deployment. Now, remote access is very similar to local access. This also facilitates rapid prototyping and deployment because you can concentrate, or your programmers can concentrate, on the system architecture, not deal with the intricacies of network programming. Writing an application that's distributed using RMI is very similar to writing an application that's local. In fact, the system architects don't need to know which parts are distributed and which parts aren't because the calls are almost identical. Now, one important thing about this is a core Java 1.1 component. Any Java implementation of 1.1 or later, revision 1.1 or later, is going to have this as a standard component. So it's guaranteed to run on any late model Java runtime. The components of the remote method invocation architecture are, there's a set of interfaces, remote interfaces. There's also a class called unicast remote object, which is used to explicitly or implicitly export objects for distribution. There are RMI registry services. The registry services are similar to a name service. It's a way of registering distributed code by name that gives a well-defined and easy-to-access mechanism for asking for a service by name and getting a reference to that object or that code so that you can call it, so that you can invoke these methods remotely. Another component is RMIC, the Remote Method Invocation Compiler. Now, even though there is no third-party language description, there's no IDL involved with RMI applications, there still is a stub and skeleton layer. And these stubs and skeletons are proxies. We'll talk about this a little bit later, but they're proxies to the actual code that's being distributed. And so the Java development kit, the JDK, also comes with this RMIC, this stub compiler, that will generate these stubs and skeletons for you without any coding. You basically just take your Java code, your compiled .class files, you run this RMIC with these as parameters, and it will output the appropriate stub and skeleton files. This is actually just a step. It's an additional compilation, which doesn't really require anything other than another compilation. Finally, we have a naming class, and this naming class is used in conjunction with the registry services. the naming class offers a set of utilities for URL type access to these remote objects. The registry service keeps names and references to these distributed objects, and you use the naming class and these URL type parameters to request these services by name. Now, in typical application scenarios, when would you use RMI for writing a distributed application? Well, the biggest answer, the most important answer for that is in a pure Java network application. If you're writing a network application that is entirely in Java, it's much quicker, much easier. It's a very simple and powerful means for quickly putting this together if you use RMI. You don't really need to worry about all of the intricacies of doing the network protocols or communication for this application. So standard applications would be like distributed chat applications or transactional applications. Well, let's look at a diagram of a simple chat application. First of all, we have the server that is hosting a distributed application or distributed object. Here it's our dispatch object. Now, this dispatch object is responsible for taking requests from clients that connect to it and distributing this information that it gets from the clients to other clients. So if you think of a typical chat application, one client is going to type a message or send a graphic or interact in some way. It's going to talk to our dispatch object, and that dispatch object is going to distribute it to all the other participants or all the other clients that are connected. So in this diagram, we notice that each of these clients has a reference to the remote object, this dispatch object. And these clients use this reference to call methods on the dispatch object, such as add message or send message, whatever the protocol for this application is. You just create a method that takes the correct type of data and distributes it among the clients. Now, second of all, we also have references to these clients that are held by the dispatch. And the reason we have this is this allows the dispatcher to call methods on the clients, sending them the information. This is a very powerful and interesting way of writing distributed applications because there's no need to pull. You don't need to write the code so that the clients keep asking some central server if any more data has come so that it can load it over the pipe. Essentially, the clients just sit there waiting until this dispatch code calls a remote method on the clients via this connection. Other typical application scenarios are Java to Corba applications, such as legacy code support. Say you want to start developing in Java, but you have a large code base that uses Corba or is written in some other language, C, C++, whatever languages Corba supports, which is most of the common languages out there. In this case, you would want to use some mapping of Java to Corba so that you can do your recent work in Java and still support your code base that's written in another application. Now, in this graphic, we see an example of that. First of all, we have our Corba implementation, our object request broker, and that uses an interface description language for its data abstraction. On the other side of the graphic, we have our Java application using its abstraction, such as the Internet Inter-Orb protocol, and they communicate via these different interfaces that abstract the data from whatever the Corba implementation is to the Java implementation, which is well defined. Finally, we have an application for processor distributed applications. Now, processor distributed applications are similar to network distributed applications, except instead of putting pieces of code that are running on different machines on a network, we're putting pieces of code running on different processors on the same machine. This can take advantage of a multiprocessor machine for applications such as number crunching or computation expensive applications. So in this graphic, as we see, first of all, we have the server, and we have an application that's sitting on top of that. And this application can have multiple processes. These can all be remote methods in remote objects here. Now, each one of these processes is essentially run on a separate thread. And each of these threads can be mapped to a separate processor on the machine, thereby distributing the processing amongst n number of processors on the single machine. Now let's take a look at the remote interfaces that make this all possible. Now what you need to do when using RMI is you need to describe some interface that is the contract with a client. It says exactly what the signature of this method is going to be. So you have a remote method that takes some type of a parameter and returns some other type of parameter. You need to declare all of this into an interface. Because essentially what the client is going to do is it's going to grab a reference to this interface. It doesn't need to know anything about the implementation. It doesn't need to know if the implementation code is in fact distributed or on another processor on another machine. It doesn't need to know any of that. All it needs is a standard Java interface that tells it what the name of any methods that are implemented by this application are, and what parameters to send them and what to expect to come back. So first of all, let's look at the top of our piece of code here. We have a public interface, MyAccess. Essentially, we've just given a name to this interface, MyAccess, and it extends remote. Now this is important. Remote is a flag. It's part of the core Java libraries. It's an interface that does not define any methods itself. It just flags this interface as being something that can be remotely distributed. Now the next part of code we have here is the public string getData. Now that is the actual name of the method that we're going to distribute. It has to be public, especially when you start talking about distributed applications. It needs to be publicly accessible, meaning it can be accessed outside of subclasses or other classes within the same package, because here we're talking about applications or clients that may be calling this that are in completely different networks. Now finally, as a catch-all in RMI applications, there is a remote exception. Now any problems that happen on the system level executing or invoking this remote method are going to generate a remote exception. So in our interface, we need to declare in a throws clause that we do throw the remote exception. Now one other important component of this is the unicast remote object class. Now unicast remote object, it's a little confusing because there's not a multicast remote object, and there may be in the future, but at this point it's the only class that you can use for exporting an object, and it can either be done implicitly or explicitly. You can explicitly export an object with the unicast remote object by calling the unicast remote object dot export object method. This will take your implementation of a remote interface and set it up for export so that client machines can get references to it and call its member methods. But you can also implicitly export an object just by subclassing the unicast remote object class. You can see there are needs for both. The simplest means is obviously to subclass unicast remote object, but what happens when you need to subclass something else, such as a thread object or some other object that you want to use for your application? So this is why we have these two different methods for exporting classes. Implementing RMI application. In this section, we're going to go over the implementation code for the interfaces that we've described in the previous section. Now let's take a look at a very simple implementation. Now in this code fragment, we start off as we would any Java class. We have a class name, the keyword class, followed by foo, the name that we give this class. Now in the next part, we extend unicast remote object. We talked about unicast remote object earlier, and we can either extend this class, in which case we get implicit export of our object, or we can explicitly export our object by calling the export object method of the unicast remote object. Now finally, this is probably the most important part, this implements MyAccess. MyAccess is the name of an interface that we've created that defines the methods that we want to make remotely available. So as far as our implementation, we have one piece of code here that says public string get data with some method body. This is the actual code that gets run anytime this method is remotely invoked. So a client gets a reference to this object, the class foo that we just created, and via that object, it gets a handle on the MyAccess interface. From the MyAccess interface, it knows that there is some method in there that returns a string that's called getData and that doesn't take any parameters, which is what we're looking at right here. So this is the black box part. This actual implementation right here is never seen by the client. This is just run on the server machine. Now, the next part that we need to deal with is the main part of our program, the main entry point. And we define this as we would any other standalone Java application. We have a public static void main that takes an array of strings as an argument. And the next part we need to address is setting a security manager. Now, in RMI, it supports dynamic loading of code. Essentially, when it needs a stub or a skeleton implementation to talk to a remote application, it needs to be loaded over a network if it can't find it locally. So we need a very special security manager to allow this without compromising system security. So the very first thing we're going to do after initializing our application is we're going to set a security manager. Now, there's a very special RMI-specific security manager called RMI Security Manager. So this is the easiest one to use unless you want to implement your own if you have site-specific needs. But right here, we're just going to create an instance of an RMI Security Manager which will allow stubs to migrate across the network without compromising any system security. The next thing we need to do is we need to bind our application with a name service. Now, we talked about the naming classes earlier. Now, naming has a number of methods for binding, for rebinding, for unbinding a distributed or remote class to a name server by name. If we look at this piece of code here, first of all, we're dealing with the naming class. So we have naming here. And the method of the naming class that we're going to talk about is bind. And what bind takes is two parameters. The first parameter is actually a URL. It looks like a normal string here, but that's because we are using defaults of URL conventions. My app is the name of the application that we're exporting. That's how other clients will ask for it. If they want a reference to our distributed class, to our application here, they will ask a name server for my app. Now here, we're not putting any of the other URL parts. We're just putting the name of the class because it's assumed that it's running on the same machine. So we don't need to tell it the name of the machine that it's running on. Now finally, we create an instance of foo. Now the class that we're dealing with here, we said class foo extends unicast remote object. So foo is the name of the class. So we're creating a new instance of this class and passing it to bind. So what's going to happen here is we're going to have a reference to the foo class, and we're going to have a name myapp. Those are both going to be sent via this naming class to our registry service. So whenever a client connects to the registry service and asks for myapp, it's going to receive a reference to this foo class that we just created. Okay, so what makes all this work? What's happening underneath? Let's first take a look at the client. Now, the client needs to bootstrap with a registry by asking for an object by name and storing it in a reference to the interface that it implements. Now, what that means is that a client is going to ask a registry for my app. It's going to get a reference for the foo class that we created, but not directly to the foo, but rather to the remote interface that it implements. So in this example here, we have my remote int m equals, and we have a cast to my remote int, which would be a remote interface. We're calling the naming class its lookup method. That lookup method is passed a string that is a URL. So in that string, we're telling it use the RMI protocol, talk to the machine foo.com, and on that registry server I want a reference to the app that's registered as my app. Now when that remote reference is returned, we're just going to store it into my remote int. Now when we want to call its member functions, you would do it as you would any local object. We just stored my remote int in the variable m, so we call m.getData, and that's going to call the getData method on our remote app. So the registry, this is our name service. Just a few more details about it. First of all, it's an RMI-specific name server. Now, it can run either as a standalone, such as a traditional port mapper or name server, or it can be compiled into an application so that an application just registers with itself. Clients can ask this application directly for a reference to itself. Now, this is a little bit more complicated because that means that the clients need to know in advance what the address is or what port number this application is running on, whereas with a registry, it runs on a well-defined port number so that all these clients can ask one well-defined application for different distributed applications that it might serve. Now, the registry takes standard URL type strings to register and also to get references to objects by name. Now, the URL conventions for this, first of all, we have a fully qualified URL here, RMI:, that's the protocol, the same as HTTP:, or FTP:, or any of the standard URL conventions you've seen in other web mechanisms or internet mechanisms. That's followed by the machine name. Here we have machine.com. Now, in the same tradition as HTTP or other type of URL, this is followed by an optional port number. Now, 1099 is the traditional or standard port number for RMI transactions. So this part can be left off as well, just like port 80 is the standard port number for an HTTP transaction. So if you leave this off, it'll default to 1099, or if you need to change it to something else, you can just put that something else here. Following the port number is a fully qualified name to the application or the object that we're interested in. Now, a standard convention is to put the package name followed by a slash followed by the name that we registered our application as. This is not necessary. You can just put a simple name here, but if you include the package name and the whole package hierarchy, there's less chances of namespace collisions. So we have a couple of simplified versions of this below, such as RMI://machine.com/class. Here we're not using, obviously, a port number, and we're not using a package name. We're just giving the class name. The next one is any call to the naming class, to any of the methods in the naming class, are going to assume you're using the RMI protocol. That's the only protocol that it speaks. So you can leave the RMI: out and just start with the // which denotes the start of a machine name. So here we have //machinename.com followed by the class. So this is another permutation. Now finally, the simplest permutation of this is just to give the name of the distributed application. So here I just have class, because if you don't put a machine name, it'll assume that the registry is running on the same machine that your application is running on. If you don't put RMI, it assumes it's the RMI protocol. If you don't put the port number, it assumes it's 1099. So in most cases, this will just do the right thing. So what makes all of this work? Now, we have a distributed object that's running on a server. We have a client that can somehow ask a name service for references to this distributed application, and once it has it, it just starts talking through the interface that it gets from the name server. So it seems sort of like magic. What's really making all this work? Now what we have here is the stub and skeleton layers. Now the stub layer is a client-side proxy to your distributed application. So when your client makes a request to a remote object, it receives not a reference to the actual object, but a reference to a stub that's dynamically loaded. And this stub is real Java code. It's a real Java class file that was generated by the RMI-C compiler that we talked about earlier. And essentially, this implements the same interfaces that our remote application implements. So our local application just talks to this stub. And the stub is responsible for ushering or marshaling all of the parameters, the return types, and sending back and forth any exceptions that are generated when this is called. Now, on the other side of that, we have the skeleton layer, and the skeleton layer is the server-side proxy. This is the part that the distributed, the service, the distributed application part, is also talking to a stub-type layer and has local type transaction with this. And this skeleton is talking directly, is communicating directly with the stub, and basically making it transparent to both the implementation of the remote object and to the client, so neither of them need to know that all this network stuff is happening. They don't need to know that parameters are being ushered to another machine or to another processor or anything else. They're just doing local type transactions. So one of the beauties about this and what makes this a really easy environment to work with is the stub compiler, or RMIC. It generates these stub and skeleton classes based on the compiled remote objects. So the implementation that we saw earlier of a remote interface, that implementation would be compiled with a standard Java compiler into a .class file. Once you have this .class file, you can generate the stubs and the skeletons simply by running the RMIC compiler on this class file. The RMIC compiler will look for the remote interfaces and look for their method signatures, their parameter types, their return types, and generate these stubs and skeletons for you. Now, this goes into a slightly different topic in that once you start dealing with these distributed object-oriented environments, you need to deal with sending objects as method parameters, and you need to deal with returning objects as return types. We're no longer dealing with just simple types because most non-trivial applications are not just passing back and forth integers or characters. They're dealing with full objects. So what we need to have is something like remote object.method new some object so that we can just send a reference to some new object to this or a copy of this. Or we also need to do something like some object equals remote object.method, in which case an object is being returned by this remote method call. Now, all of this, this whole environment here requires object serialization. What object serialization is it's a technique for representing objects, which are abstract things, as a serial stream of bytes. What object serialization does is it gives you a copy by value. What that means is when you create an object and then serialize that object, it doesn't actually move the object somewhere else. The object still exists here, but it creates a serial representation of that can be sent over an object stream. And this is a standard input or output stream in Java that has been extended to handle object types, serialized object types. Now, this allows object state persistence, such as taking an application or an instance of an object that is modified, the field values are changed, and you can just write the whole object out to a stream or to a network connection and read it back in and read all that state in. So this is actually a very powerful thing. Another important thing about object serialization is it allows you to hide data, because sometimes you don't want to send all of the values. Sometimes there may be local or special protected data that you don't want to migrate to other machines. And you really need to be able to protect these in a distributed system. So in the Java model, you can either mark a field as transient, in which case it won't be serialized when the object is sent over the pipe. A default value will be initialized when the object is reconstructed on the receiving end. Or you can state that it's static, in which case you get the same behavior. It'll be initialized on the receiving side as its default state. Now, all of this required some extensions to the java.io package. First of all, most of the base classes are now serializable in java.io. Essentially, all the classes that make sense to be serializable. Some of them which represent local resources don't really make sense as a serializable object, in which case they're not. And all of these objects are marked serializable by simply implementing a flag interface called serializable. And this is part of the java.io package as well, java.io.serializable. And any object that implements this can be sent over a network connection. Now, there is a default serialization that happens if you simply implement this interface, but you can also define your own read and write object methods in a class in case you want to do some special processing or do something other than default serialization. The only thing that matters is your write object will take all of the data from your object and write it to a stream, and it's important that the read object can read that data back and reconstruct the object's state. So as long as your read object and write object match, you can define your own in any arbitrary object. Now, an object stream can be a file handle or a network connection or any other stream type object. So there's a lot of use for this for sending an object either across a network, as in our distributed applications, or sending it directly to a file, which is also a very useful thing to be able to do. Overview of CORBA. In this section, we're going to review the Common Object Request Broker architecture. Now, CORBA is a language-neutral system for distributed applications. Now, this is a key component of CORBA. This is a very important note to make. CORBA is not bound directly to any language, such as C or C++ or Smalltalk. And since it deals with these different types of applications that may have very different transactional models or data representations, it requires some abstraction that will map these different environments. So CORBA uses an interface description language, or IDL, to define the object structure and semantics, as well as the parameter types and representation for these different systems. Now, IDL components are portable across languages and tools and operating systems and networks. They support callbacks and dynamic invocations. Now, some typical application scenarios. First of all, if you're supporting a non-Java, or more importantly, a non-homogeneous environment or non-homogeneous platforms, or you need to support legacy code that is written in C or C++ or Smalltalk, then it really makes sense to use CORBA because it's not tied directly to any of these, and all of these different environments can be mapped directly to it. So applications that require object-oriented distribution that are not written entirely in Java or will need to use non-Java components in the future really are prime candidates for applications development using the CORBA architecture. Let's take a quick look at the CORBA structure. Now, we have a multi-level diagram here that starts on the bottom level with general service interfaces. Basically, this is what the whole system is sitting on top. This is its interaction with your operating system. Now, the next layer up is we have the ORB, the Object Request Broker. Now, this Object Request Broker is talking both to clients and servers that are dealing with different code bases written in C, C++, or Java, all by these interface description language, or IDL, mappings. Now, for a slightly higher view look, let's look at this with our three top mappings. In this graphic, first of all, we have a set of common facilities, a set of domain facilities, and a set of application facilities that all sit on top of this object request brokers. Now, first of all, in the common facilities, these are facilities that are accessible by a wide variety of applications. These are system-level facilities such as printing, document management, email, etc. Now, the second section here are domain interfaces. Now, these interfaces are geared primarily towards vertical markets or field-specific things such as financial applications, medical applications, engineering, etc., various vertical markets. And finally, we have the application interfaces. What the application interfaces are the user or application-defined interfaces. This is really where the reusable code part comes in. We have all these different application-specific pieces of code that are part of our whole model. Now, all of this works using what are called interface repositories. This is reusable application code that facilitates dynamic requests. Interface repository is essentially a database of interfaces that can be used for creating these requests to an org. As you see here in this graphic, we have a model of an interface repository. On the top of the diagram, we have our client. Now, our client either talks via an IDL connection or through a DLL, or dynamically linked library. Now, first of all, if it goes through the IDL, then the stub for our object constructs a request and passes it on to the orb. But on the other side, if we use the DLL, then the DLL can get an interface from the interface repository that we see is hanging off of our object request broker. Now, based on that interface that it got from the orb, it constructs a request, and then it passes that request to the orb for processing. Now, Corba allows either statically or dynamically defined method invocations. You can define these at compile time so that you can either have strong type checking, thus minimizing bugs, semantic bugs rather than syntactic bugs, or you can maximize flexibility. Now, there are very high-level language bindings in Corba. This allows you to choose the high-level language that you want for the actual implementation of the code. Now, this is all mapped back to Corba through an IDL, or interface description language. This is a self-describing system. There are provisions for runtime metadata for describing every server interface known to the system. So Corba orbs support this interface repository that contain information describing functions that a server provides and the parameters for these functions. Now, local versus remote transparency. An orb can run as a standalone, or it can be distributed over a network. So objects interact the same whether they're remote or local. Thus, we have the transparency. To the programmer, to the person implementing the system, it doesn't matter if it is a local application or a distributed application. We have this local versus remote transparency. Corba also supports security and transactions. There's a full built-in transaction model, and the system contains context information to handle security and transactions across machine boundaries. Now, interoperability with existing systems. This IDL, this is really the magic, the glue in a Corba system. This allows the abstraction layer for mapping Corba with existing systems or with future systems. Now, so we've talked a lot about this interface description language, IDL. So what is this? Essentially, it's a contract between the client and the server. It's the server saying exactly what the interface, what the face on the world is for its application. And it's also doing a mapping. It defines the types and transactions in a platform-neutral way. So it doesn't matter that one machine is a big Endian 32-bit int and the other one is a little Endian 64-bit int. The data representation doesn't matter. It's all mapped via this interface description language. So finally, to wrap up our overview of Corba, let's just take a look at a very simple IDL file. Here we have counter.idl. Essentially, this is just an accumulator. Now, this IDL is a module, and we have to give it a name to refer to it. So in the first part of our code, we have module counter. And this is using an interface that we're going to call count. Now, the attributes for this, we have attribute long sum. This is saying that we have some field, some variable in this object called sum that is a long integer. And the next part, long increment with the parentheses, this is saying that we also have a transaction or method call called increment that returns a long. And just by looking at this interface, you can assume that this application is going to maintain, first of all, a number of how many times it's been incremented and store that in sum, and it's going to have an increment function that allows you to interact with that field. Now, as you can see from this very simple IDL file, it's a simple and high-level mechanism for mapping different types of systems all to a well-defined, simple interface description. And this is really at the core of how the entire Corba architecture works. Corba in Java. In this section, we're going to talk about the mappings and the interoperability between Corba systems and Java systems. First of all, we're going to map the interface. Now, we looked at an IDL in the previous section that described an incrementer, a counter. So here is the Java version of that interface. First of all, we have interface count extends Corba.object. Now, this is followed by a simple method description. This is very similar to the method descriptions we saw in the remote interfaces earlier in this program. Here we have public int sum, which throws a corba.system exception. This is the equivalent in Corba to the RMI exceptions that we saw earlier. Following this, we have public void sum int val. This is so we can pass a value to our sum. And finally, we have public int increment, which is the implementation of our incrementer function that we described in the IDL. So when we want to actually implement this interface, here's a code fragment from a class description. First of all, we have the implementation of the increment function. We've got a body with some code that does the incrementation. We've got a sum method, which is just our access operator for getting to the sum, passing it a value. And we've also got the int sum with no argument with some operations that we'll define when we implement this class. Now let's take a look at the Java IDL packages, or packages that have been added to Java to support Corba. These have all been supplied by OMG, or the Object Management Group, which is an umbrella organization that oversees the Corba architecture. Now, first of all, we have a base package, org.omg.corba, which defines all the base classes and interfaces that we need to make this work. We have an orb package, a type code package for type mapping, portable. We have a naming package, which has very similar utilities to the naming system that we saw in RMI. Now, these classes, there's a number of different types. There are holders and abstractions for data types. There's exception classes, flags, constants, attributes. There's a number of different types of classes that support the various incarnations or abstractions that you use in the Corba system. Now, an example IDL using the Java Corba mappings here looks almost exactly the same as standard Java code. The only difference you'll notice here is the keyword module. We have module coming from the Corba IDL that we saw earlier. Otherwise, this looks pretty much like standard Java. We have module hello app. That's followed by an interface hello. And that interface is describing one single method, say hello, which returns a string. Now, let's take a look at some example server code. We're going to walk through the Java code for implementing a server that uses these Corba packages. Now, on the top of our code, we're going to first import hello app, which is our interface. We're going to import the naming class, cosNaming, which is our naming service for our Corba application. We're going to import the naming context, and we're going to import the base Corba classes. Now, once we've gotten all the importation done, included all of these packages we need to use, we'll get into the actual code here. Now, first, our class hello server is going to extend our hello implementation base, which is a base that we'll create a little bit later. Now, this base is going to implement our say hello method that we saw previously that returns the string. So here's the actual code implementation that returns the string hello world. Very simple application. So now in our constructor here for our hello server, we have a standard class description, public class hello server. We're going to put a main method in it, the same as we did in our RMI application, a public static void main that takes an array of strings. And first, we're going to put in a try clause our Corba setup. So we're going to put our try here so we can catch any exceptions that are generated when we try to initialize our Corba stuff. So first, we're going to create and initialize the orb. We're going to take an orb object that we got from our Corba package, and we're going to call its init and pass it a set of arguments. Now, after we've created that, we're going to register it with the object request broker. So here we have hello server.hello ref equals new hello server. So this is actually going to create a new instance of our Corba object, and it's going to assign it to this hello ref. Now we need to grab the root naming context. We're going to use this context for actually grabbing a reference to an object by name. So first we are going to grab the root with an org.omg.corba object ref, and we're going to assign that the return value of resolve initial references that is a method of the orb object, and we're going to pass that the name of our root name service. Here we call it name service to be simple. Now we're going to use that reference that we got from this method call, and we're going to pass that to a naming context helper .narrow method, and that is going to return our naming context that we're going to store in the NC ref. Next, we have to bind the object reference in our naming class. So first, we're going to create a new name component. We're going to call it hello, and we're going to assign that to NC, which is a name component object. Now, name component, we are going to take that to rebind it to our server with our hello ref, and we're going to assign that to an array of name components that we're calling path. Now, we need to set up our code for waiting for our client invocations. Now, first of all, we're going to create a sync object. Basically, this is used for just marking pieces of Java code. This is a standard Java convention for synchronizing code that's not necessarily directly in a method call. So we're just going to create a java.lang object sync, which equals a new java.lang.object. We're going to say synchronized sync, which gives us the synchronization methods. And then we're going to put a sync.wait in there that causes the thread to wait. And we're going to finally end our try clause with a catch clause here that's going to catch an exception E and print out the errors if there were any Corba or other errors or exceptions that were generated while this application was running. Now, it's a very simple application, but let's look at the client implementation. The client needs to somehow get in contact with this server and interact with it. So let's take a look at that code now. Now, first of all, we have similar imports on the top. We're going to import our Hello app interface and our naming package and our Corba package. And when we get into the code, we're first of all going to call our client Hello Client. Now, this is also going to have a main method, public static void main, which also takes the array of strings as an argument. And again, we're going to have a try catch clause. First, we're going to create and initialize our client orb. So we take orb equals orb.init and takes the args from main, same as we did in the server. The next thing is we need to get the naming context the same way we did with the server, only this time we're not going to register ourselves. This is so we can get a reference to that server. So we're going to store that object ref in the objref, objref variable name. We're going to pass it the same name service to our resolve initial references method call. We're going to take the return value of that and get the narrow reference name to it and store that in ncref. Finally, we're going to resolve the object reference using our naming class. We're going to say name component nc equals new name component and pass the name. And we're going to get the return values of that and pass that to our hello helper.narrow and pass our ncref.resolve followed with our array of paths that we got in the previous method. So now once we have all this set up, we can call the hello server object and print out the results. So to do that is really simple. It's almost as simple as the RMI model. We have a string hello equals our hello ref.sayhello, which calls that method. So then we get that return string. We assigned it to the hello field, and we're just going to print it out using a simple system.out.println.hello or parentheses hello. So it's very simple. It's almost as simple as the RMI model. And just to clean up, we're going to close our try-catch clause. We're going to catch any exceptions that were generated and print out error messages if they occurred, and we're going to close up our method. And that's essentially it. Now I want to move on and talk briefly about the Internet Inter-Orb Protocol, or IIOP. And essentially, the Internet Inter-Orb Protocol is this whole model of Corba going across Internet clients. So we have an Internet-based Corba model. And this model preserves state across invocations. It supports the IDL as it has to in any Corba implementation. It supports the same interface repositories. It supports metadata. dynamic invocations, the transactions, the same security model and callbacks, and all of the IDL defined methods that we've seen in raw Corba and in the Java IDL. Now finally, RMI over IOP. How does this all tie together? Well, originally, JavaSoft had made a clear distinction between RMI and Corba and saying there are two different things and there's not going to be any interactivity. If you want to use Java for distributed applications, you use RMI. If you want to do anything else, you use Corba. But eventually they lightened up their stance and made an announcement that they would support IIOP as a swappable layer, a lower layer of RMI. And what this is going to allow you to do is use RMI on the Java side of a distributed application and use Corba via IIOP on the non-Java side of it. And this is a really interesting thing. It'll be available in a future Java development kit. It's going to have the very same semantics on the RMI side that RMI developers are used to. And on the Corba side, it's going to have the same semantics as the Corba users are used to. So it's really a marriage between these two different object systems, the homogeneous and the heterogeneous, that ties this whole system together, allowing C++, C, Smalltalk, Scheme, whatever, other applications to all nicely fit in together in a distributed application environment and coexist with Java. Now let's review what we've covered so far. Now first, what is the difference between a traditional procedure-based distributed application and an object-oriented distributed application? Now in RPC, there's no need to create an instance of an object. It's a procedural-based application. Whereas in an object-oriented model, you need to use objects as parameters, and you need to facilitate object migration, as well as handle object method calls. Give three distinguishing features of RMI. It's a pure Java solution. There's no interface description language. Remote access is similar to local access. What are stubs and skeletons? Stubs and skeletons are proxies to distributed objects in both RMI and Corba implementations. Name the three facilities of the Corba abstraction model. They're the common facilities, the domain interfaces, and the application interfaces. Describe local versus remote transparency. Now this is what allows distributed code to look like local code. Essentially, a developer doesn't need to know that the code they're interacting with exists on the same machine or on another machine. Why use an IDL? In a heterogeneous environment, you need to map data types between environments. Thanks for joining us. I hope you've gained some useful information and found this to be a useful program. If you need to contact me, please try the URL http://www.webcal.com/Downing. Or for more information, you can pick up my book, Java RMI Remote Method Invocation, published by IDG Books. Thanks for joining us.